Welcome to The Explainer. Today we're taking a highly technical journey, literally deep into the silicon. We're going to look way past the standard marketing numbers to examine the hard physical limits of processor architecture. And, more importantly, we're looking at the brilliant engineering hacks used to bypass those limits.
Here is our architectural stack for today: the physical limits, multi-level cache hierarchies, superscalar out-of-order execution, advanced branch prediction, the TAGE predictor, and finally, heterogeneous architectures. Let's get to it.
So, let's dive right into the fundamental tension of modern hardware. For decades, the industry just rode the wave of Moore's law, right? Doubling transistors every couple of years. But what happens when cramming more transistors and cranking up the clock speed physically starts melting the chip? And even worse, what happens when the processor becomes so blazingly fast that it spends all its time just waiting for data from main memory? Well, that tension is exactly what drives all modern processor architecture.
Section 1. The physical limits, the end of Dennard's scaling and the memory wall. To really understand our current limits, we've got to respect the history. Just look at this incredible exponential curve. We went from the Intel 4004 back in 1971 with a mere 2,300 transistors all the way to the Intel 486 in 1990, hitting over 1 million transistors with a 5-stage pipeline. By 2001, we entered the gigahertz era, scaling up to 100 million transistors. For a long time, this strategy was almost too simple. Shrink the transistor, increase the clock frequency, and just enjoy the free performance gains. But cramming that many switching elements into a tiny silicon die meant processors were literally approaching the heat density of a nuclear reactor core. We hit a massive thermal wall.
And this breakdown brilliantly illustrates why that specific era ended. You see, you can't just keep raising clock speeds because power consumption scales non-linearly. Pushing higher clock frequencies actually demands a cubic increase in power. It's just thermally unsustainable. So this physical limit forced a massive architectural pivot. Engineers shifted heavily toward wider SIMD execution, which only gives a linear increase in power, and multi-core designs, which have a quadratic power increase. These were simply much more efficient ways to use that silicon real estate without completely burning up the chip.
Section 2. Multi-level cache hierarchies, overcoming the memory wall. Okay, so once you have a fast multi-core processor, you almost immediately slam right into the memory wall. A processor is ultimately only as fast as the data you can feed it. To hide the massive latency of main memory, we rely on caches. But as we know, caches aren't perfect. To optimize them, architects rely on Mark Hill's famous 3 Cs model. First, cold misses. These are inevitable. It's simply the first time the program asks for a specific piece of data. Then, capacity misses. These happen when your cache just isn't big enough to hold the program's working set. And finally, conflict misses. These happen when your cache mapping strategy forces 2 active blocks of data to fight for the exact same slot in the cache. Now notice the really harsh engineering trade-offs at play here. You can't just fix one mistype without impacting another. For instance, if you increase the block size, great. You beautifully decrease your cold misses because you're fetching larger chunks of data at once. But look at the resulting impact. You likely increase your capacity and conflict misses because larger blocks inherently mean fewer unique blocks can fit in the cache at the same time. It's this constant, delicate balancing act of capacity, block size, and associativity spread across multiple cache levels. Moving on to Section 3, Superscalar Out-of-Order Execution, Maximizing Instruction Throughput. Let's assume our cache hierarchy actually did its job and the data is ready. How does the core maximize throughput? Well, it does it by breaking the rules of sequential programming. The out-of-order core is essentially a micro data flow engine. First up, instruction dispatching. This is where complex instructions are broken down into simpler micro-ops. Second is execution. Instructions are tossed into reservation stations. They just sit there, out of order, waiting for their data operands to arrive. But the exact moment that data is ready, boom, they fire into the execution units. Finally, to maintain program correctness, which is absolutely crucial, instruction completion uses a reorder buffer to retire these microops exactly in their original program order. So the really tricky part is how we handle dependencies. If instructions execute out of order, they might accidentally overwrite a register that a delayed, older instruction still desperately needs to read. We call these false dependencies, specifically write after read and write after write hazards. The processor solves this brilliantly on the fly using register renaming. It dynamically maps the limited number of architectural registers, the ones defined by the software, to a much larger hidden pool of physical hardware registers. This elegantly removes those bottlenecks and lets the execution units just run at full tilt.
Section 4. Advanced branch prediction, the key to speculative execution.
An out-of-order pipeline is incredibly powerful, no doubt, but conditional branches, those are its Achilles heel. A pipeline stall here is fatal for throughput. To prevent this, we use speculative execution based on branch prediction. Now, early processors used simple Smith predictors. These were basically 1-bit or 2-bit counters tracking only local isolated branch history to guess taken or not taken. But come on, real-world programs are way more complex than that. So, Ye and Pat introduced two-level adaptive prediction. Instead of just looking at the branch in total isolation, it uses a shift register to track the dynamic history of previous branches and uses that specific contextual pattern to index into a separate history table.
We can actually categorize these two-level predictors by their granularity. GAG is kind of the bluntest instrument, using a single global history register to index a global pattern table. PAG gets a bit smarter, using per-branch history registers to index that global table. But PAPs, that is the ultimate granular approach, using per-branch history indexing into per-branch pattern tables. By capturing these distinct, dynamic execution contexts, prediction accuracy absolutely soared, pushing well past 95%. Section 5. The TAGE predictor, state-of-the-art branch prediction. Now, what makes TAGA so remarkable as a state-of-the-art solution is exactly how it scales history. It uses a fairly simple base predictor, but backs it up with multiple tagged predictor components. The clever part? These components are indexed using global history links that form a geometric series. This means most of the storage is dedicated to short, recent branch histories, but the predictor is still highly capable of capturing correlations with branches that executed literally thousands of cycles ago. But TAGE alone isn't perfect, and honestly, the lengths hardware engineers will go to squeeze out every last drop of accuracy is just fascinating. Modern implementations attach highly specialized side predictors to the main engine. For instance, the immediate update mimicker steps in to fix predictions using data from branches that are currently in flight but haven't actually retired yet. The loop predictor specifically catches loops that have constant iteration counts, and the local statistical corrector tracks those really annoying branches that don't strongly correlate with the execution path but still exhibit a reliable statistical bias over time. And here is the true genius of TAGE for hardware engineers. High accuracy normally means a heavy silicon footprint, plus a severe power drain from constant multi-port table accesses. But by actively eliminating unnecessary reads on correct predictions and utilizing four-way interleaved single-ported memory banks, a TAGE predictor averages an incredibly efficient 1.13 table accesses per retired branch. It achieves absolute state-of-the-art accuracy without melting the power budget. It's a huge win. Finally, Section 6. Heterogeneous architectures, beyond the homogeneous core. So what happens when optimizing the traditional CPU core is no longer enough to keep up? Well, we go beyond the homogeneous core. We start building massive systems on a chip that combine standard CPUs for general-purpose control flow, GPUs for massive parallel processing, and highly specialized domain-specific accelerators, all sharing the exact same piece of silicon. A really prime example of this is the Google Tensor Processing Unit, or TPU. Think about the crazy complex out-of-order CPU we just discussed, with its advanced branch predictors, reorder buffers, and register renaming. The TPU throws literally all of that away. It uses deterministic execution. By completely ditching the dynamic out-of-order logic, it frees up massive silicon space to build a systolic array. This allows the TPU to perform an astonishing 65,536 multiply and add operations in a single cycle. It's a perfect illustration of how architecture ultimately dictates performance. You have general-purpose complexity on one side and massively parallel deterministic efficiency on the other. Architecture dictates performance, absolutely. So, as we look to the future, the ultimate question is, how will your software adapt to fully leverage this incredible, heterogeneous silicon? Think about that. This information brought to you by Microdyne Computers. If you enjoy the content, please consider giving a like and subscribe. This helps me understand what viewers like you want to see. Thank you so much for watching.